Okay, today we take ice tables to a whole new level. So we are studying today the quantitative changes in equilibrium systems, so calculations. I've written a series of steps here to help you as a guide. Might not mean much until we actually get into some examples, but we definitely start off by writing a balanced equation and then constructing the ice table. Now, so far, the calculations we've been doing for ice tables are fairly simplistic in that we can calculate initial concentrations by using C equals N over V, and if a certain substance is not mentioned, we assume the initial concentration is 0. And then for the change row, we assign positive and negative. We figure that out by whichever side has 0, that's the one that is going to increase in concentration towards equilibrium, and whichever side has an amount to start, that concentration will decrease approaching equilibrium. Now, what if the initial concentrations of the reactants are not 0 and the initial concentrations of the products are not 0? Then we're going to have to use the expression for K, but instead of equilibrium concentrations, we're going to substitute initial concentrations and calculate something called Q, the reaction quotient. Q, you'll see here, is the exact same formula as K, except we're plugging in initial concentrations instead of equilibrium concentrations. When we compare the value of Q to K, we can determine which way the reaction is proceeding towards equilibrium. When Q is greater than K, that means that the ratio of P over R is too large. It has to get smaller in order to approach the value of K. So how does the value of this quotient decrease? Well, our numerator has to get smaller and our denominator has to increase. That will decrease the quotient, the value of the quotient. For example, if you had 3 over 4, which we know is 0.75, if you wanted this value to get smaller, to decrease, if you decreased your numerator and increased your denominator, then 2 over 5 would be 0.4. So can you see how we've gone from 0.75 to 0.4 by having the numerator decrease and the denominator increase? And so if Q is already greater than K, then we need Q to start decreasing. In order to get the value of that quotient to drop, the numerator has to drop and the reactants, the denominator, has to increase. And that means that the reaction is really proceeding from right to left. We'll construct an ice table in a moment to help you with that. Conversely, if Q is less than K, then the reaction is proceeding left to right because it's the numerator that has to increase and denominator decrease in order for the value of the quotient to become larger and larger until it equals K. If you go back to your bean activity from the very first lesson activity in the unit, you can take the ratio of P over R for each step in the activity in your table, and you'll notice that that value of Q is changing until it gets to K, the value where it holds constant. Okay, as far as the steps in the overall reactions here, or in the overall problem, you'll follow the mole ratio to finish that change row. So if you've already decided on the positive or negative, if the coefficient's 1, you might say plus 1x. If it's 2, it might be minus 2x. I say might because it depends on the sign, but definitely the number here, 2, follows the mole ratio. If that's the coefficient, we put a 2. If the coefficient's a 1, we put a 1. Okay, following steps 1 and 2 then, which is basically building that ice table, we'll write an equation for K, and now it depends on the question. If you are given K, you may just be substituting equilibrium concentrations and then solving for X. And if that's the case, we'll have 3 different methods. We'll check perfect squares first of all. That'll make it for a quick solution. If that doesn't work, we'll try an approximation, which can really simplify the math. And when all else fails, we'll use the quadratic formula. So I'm expecting that the quadratic formula is super familiar for you from math. So if you need to, go back and review your math work from, I believe it's grade 10 actually, where that's first introduced. Okay, and if you have been given the equilibrium concentrations or able to figure those out, then you'll just be able to calculate K. So first off, I'm starting with 4 questions here, A, B, C, and D, where I just want you practicing building the ice tables. So use the given information to complete ice tables for this equilibrium system. I'm telling you that K equals 57 at 700 Kelvin, but really what's relevant here is that you have the balanced equation and you take the given information and start constructing your ice table. So begin with your balanced equation and set up your ICE. So I've written the balanced equation, set up the ice table, and started to calculate initial concentrations. So this should actually be familiar for you from the work we've already done. So I would pause the video and complete the ice table, then check back. Okay, so you can see that I completed the initial concentration row. There's no HI mentioned, so I started with 0 there. And then I show the change happening where the HI needs to increase since it's starting at 0. And I follow the coefficients. So 2x here, minus 1x, minus 1x. And now I plus C equals E. So 0.20 plus negative 1x is just minus x. Same thing here, 0 plus 2x equals 2x. So we're not solving a large problem in these initial examples. I just want you practicing building ice tables. If you can build the ice table, there's not too much more to the chemistry of it, and after that it's just working the math. So try the second question here. Again, it's the exact same equilibrium system. Now a 2-liter flask contains 0.4 moles of HI. Okay, so you'll see that I started off with 0 on the H2 and I2 because they were not mentioned, and calculated the concentration of the HI initially. Again, I follow the coefficients in the balanced equation at 1, 1, and 2 for the 1x, 1x, and 2x. And the concentrations of H2 and I2 start at 0, so they must increase, the plus x, and HI will decrease. And so I plus C equals E, and I write the algebraic expressions for the equilibrium concentrations. Okay, let's try the next one. So set up your ice table and your initial concentrations and see if you can decide which side is the plus and which side is the minus for the change row. Okay, so I've constructed my ice table by calculating the initial concentration, C equals N over V, for all 3 substances. Really, at this point, it's hard for me to decide which side is increasing and which side is decreasing. And here's where in those steps, I said that if the concentration of the reactants and products initially are not 0, then we'll need to calculate Q and compare to K. So just to jot it down because it's not on the screen anymore, in the original question I said that K was equal to 57. So we calculate Q using these initial concentrations and the expression for K. So expression for K, concentration of HI squared over the concentration of H2 times I2, and we can substitute 0.4 squared over 0.02 and 0.05. And so now we go ahead and calculate Q. So Q equals 160. Now how does Q compare to K? Q is 160, K is 157, so Q is greater than K. Therefore, the reaction is proceeding from right to left towards equilibrium. What proceeding from right to left means that the HI is going to be dropping and the H2 and I2 will be increasing. So remember, when Q is greater than K and the value of that quotient has to drop, that means that the product or numerator has to get lower and the reactants or denominator have to increase. So which reaction decreases the products and increases the reactants? The reverse reaction, and that's why I'm subtracting on the product side and adding on the reactant side. So why did we have to calculate Q when we didn't have to do that in A and B? Because none of these are 0 to start. So when you have concentrations of all the entities in the reaction, then you need to calculate Q and determine which way the concentrations are changing. Okay, so now we follow the mole ratio of 1, 1, and 2, And so we have plus x, and minus 2x. So our expression here is 0.02 plus x, 0.05 plus x, and the concentration at equilibrium for the HI will be 0.4 minus x. Okay, so that was some practice there. Now try part D, it's the last one of building the ice table, and apply the same concepts, just what we did in C. Okay, so you can check your work. I started off with the equation, set up the ICE, did the initial concentration calculation, 0.1, 0.3, and 0.1. Here they are. And then recognizing that none of these were 0, I didn't know which way it would proceed towards equilibrium. So to decide on the minus minus plus here, I calculated Q and compared it to K. So Q was less than K, and so the reaction proceeds left to right, which means that these will drop and this one will increase. Here's my final algebraic expressions for the equilibrium concentrations. Okay, so now we'll go into examples that involve all of the steps that I wrote at the beginning of the lesson. So here we go. Number 1, 0.100 moles of H2 and I2 are mixed in a 1 liter flask. After a period of time, equilibrium is reached. It was found that the concentration of I2 decreased to 0.020 moles per liter. Find K. So start with an ice table. Fill in everything you can. Okay, so here's the ice table. I did not show the calculations for the initial concentrations, but just to refresh your memory, N divided by V. Okay, so we were given the equilibrium concentration of I2, and so I filled that in right here. So now if I do I plus C equals E for I2, so the equation here for I2, 0.10 minus x will equal the 0.020. So here's an equation where I can solve for x. So go ahead and solve for x here and then calculate the concentrations of H2 and HI at equilibrium, and then move on and calculate K. Okay, just in case you're getting stuck at the further steps, I'll just say what's happening here. I have taken the value for x, and when I was isolating x, I noticed that I had negative x on the left side. So if I swing that over to the right, it will be positive x. Then I'll bring the 0.020 back over to the left and subtract, and I finish with x equals 0.08. So the equilibrium concentration of H2 is given by this expression. Now I know what x is, so substitute the value of x and calculate the equilibrium concentration of H2. Same thing with the equilibrium concentration of HI. Okay, the instructions were to find K. So the last step is to now write our equation for K and then calculate K, substituting in those equilibrium concentrations. So try that now and check your answer. All right, so I substitute the equilibrium concentrations into the expression for K and calculate that K equals 64. Okay, moving on to example 2. We're given an equilibrium system, told the value of K, given the initial moles of substances in a 2.5 liter vessel, and asked to calculate the concentration of XY at equilibrium. So this question is going to run a little bit differently in the end from example 1, but nonetheless we still write our equilibrium, write our balanced equation, and set up our ice table, and then see what we are going to solve for in order to find the required information. So set up your ice table. Okay, so in setting up the ice table, I calculated initial concentrations and then realized that nothing was 0. And so I needed to calculate Q and compare that to K in order to decide which way I should be increasing and decreasing the concentrations. And you'll see that I've come up with Q value greater than K, and so the reaction proceeds right to left towards equilibrium, and now I have my equilibrium expressions. Okay. We're asked to calculate the concentration of XY at equilibrium. So we really need to know the value of this expression right here. And in order to calculate that, we need to know x. So if we don't know what x is, this is where we use the expression for k and substitute all three of these equilibrium expressions and then solve for x. So we'll start with that. Write yourself an equation for k, substitute the k value here and each of those equilibrium expressions, and then we'll talk about solving for x. Okay, so I wrote the equation for k and substituted the value for k as well as the equilibrium expressions. They happen to be binomials. So that's it for the chemistry. The rest of this question is about solving for x. So we have three different strategies that I summarized at the beginning of the lesson: perfect squares, an approximation, and when all else fails, the quadratic formula. So let's check perfect squares. Can we take the square root of both sides here? Well, the square root of 0.018, our calculator can do that for us. Can we take the square root of the right side? Well, we have in the numerator something, 0.15 minus 2x, being squared. And in the denominator, we have 0.20 plus x, quantity squared, right? There's two of those factors here. And so we can take the square root of both sides. And so that's the strategy here. Take the square root of both sides. And in doing so, we'll have here the square root of 0.018. I don't recommend you pull out your calculator until the very end. And then we take the square root of, just the same way that the square root of, box squared over triangle squared, the square root of that would just be box over triangle. So that's what we're doing. The square root of all of that on the right side is going to be 0.15 minus 2x over 0.20 plus x. Now, why was that so helpful? Well, it's eliminated the quadratic nature of this equation. And so we won't need to solve a quadratic, it's just a linear equation. So at this point, we're going to multiply on both sides. The goal is just to isolate x. So if you think you know what you're doing, I would pause the video and move on and do it yourself. I realized I'm missing a little bit of space here. I'll just slide that over. So I'm going to multiply on both sides by the denominator of 0.20 plus x. That'll cancel it here. And now the square root of 0.018, again, is just a number. So I'm going to, it's like, what would you do if you had 2 times 0.20 plus x? Wouldn't you just distribute that 2? So that's exactly what I'm going to do here, distribute there. So I'll have the square root of 0.018 times 0.20, which actually, if you've worked with radicals, we'll write the number without the radical in front. Okay, plus x times the square root of 0.018. And that will be equal to our right side of 0.15 minus 2x. Okay, now I'm looking to collect like terms. So I notice that I have an x term here and here. So I want to make the x terms positive, so I'm going to swing the minus 2x over to the left side to make it positive. And I'll bring the constant term here, I'll bring that over to the right side and subtract it. Okay, at this point, I look at the left side and I know I'm looking to isolate x, so I'll notice that I have a common factor of x. So I'm going to pull that common factor of x out of the binomial, and I'll be left with the square root of 0.018 plus 2. And on this side, I have this left. Okay, so now I'm trying to get x by itself, and right now it's x times a number. That's really what square root of 0.018 plus 2 is. It's just a number. So I'm going to divide on both sides by what's in those brackets. The square root of 0.018 plus 2, the square root of 0.018 plus 2. So they'll cancel on this side, and x is now by itself. So at this point, I would pull out my calculator and input open bracket 0.15 minus 0.20 square root of 0.018 close brackets divided by open bracket square root of 0.018 plus 2 close the brackets equals. And so we've solved for x equals 0.058. The original question was to calculate the equilibrium concentration of the HI, which is up here, and so that's what we can finish with now. So I'm going to calculate the equilibrium concentration of HI from this expression now that I know the value of x. So 0.058 can be substituted there and subtracted. 0.15 minus 2 times 0.058 leaves us with 0.034 moles per liter. So therefore the equilibrium concentration of HI is 0.34 moles per liter. Okay, all the problems run very similarly. It only comes down to the math. Can you take the perfect square, or is there an approximation to be used, or do we need to use the quadratic formula? So I need to rearrange the questions a bit to leave myself some space for question 3, but you can start by copying down example 3 and set it up as far as you can and try to solve for x. So at this point I've set up the ICE table. Now I'm going to write an equation for k, substitute this value of k. Actually, you know what? That's going to be a lot to keep writing out, so I don't think I'll substitute k until the very end. But I will substitute the algebraic expressions for the equilibrium concentrations. So you can go ahead and do that and check in with the video. Okay, so at this point I need to solve for x, and yes, k has a number. It's 1.60 times 10 to the negative 5, but that's a lot to keep writing out. So I'm not going to actually substitute that value of k until I need to use my calculator. So first I look at the perfect squares. Can we take the square root of k? Of course, that'll just be a number from our calculator. Can we take the square root of the right side? Well, you'll notice that 2x is being squared, and this binomial is being squared, but this x here is not being squared, and so we cannot take the square root of both sides. So actually what's going to happen when we square 2x, we'll end up with 4x squared, which is then going to multiply by x, and suddenly we have a cubic to solve. All right, well, when the perfect square doesn't work, then any binomial you have in the equation, you can check to see if x is so small that subtracting 2 times x from 0.40 is really approximately the same as 0.40. So the approximation works like this. You check to see if the initial concentration divided by k is greater than 100. That's what you're checking for. So the initial concentration in this binomial here is 0.40. You can see it came from the I row right here. So we check to see if 0.40 divided by that k value of 1.60 times 10 to the negative 5, we check to see if that is greater than 100. So go ahead and punch that into your calculator and see. So hopefully you see that that value is 25,000, and that indeed is greater than 100. And so the value in that is that that binomial 0.40 minus 2x, by that approximation holding true, the 0.40 minus 2x, x is so small that that binomial, even when you know the value of x and plug it in, it's still going to be approximately 0.40. And so this denominator here, I'll square the 2x, but this denominator here essentially just becomes 0.40 squared. So you'll notice I just omitted the minus 2x based on this simplification here. And in doing that, it's true, I still have a cubic. However, I only have an x cubed term, right? The numerator here is 4x cubed. And if I multiply on both sides by the 0.40 squared, then I'll have 0.40 squared times k, right? I can divide on both sides by 4, and then eventually take the cubed root of 0.40 squared times k divided by 4. So here's where we can actually go and substitute in our value for k now. So 0.40 squared, right, that's being squared, times the value for k, 1.60 times 10 to the negative 5, all divided by 4. So you'll want to use your calculator and take the cubed root. I would recommend that you open brackets and do your you're going to need to open brackets to begin with, and then your 0.40 squared times 1.60 exp negative 5 divided by 4, close brackets. Now we'll have needed the cubed root, and so you probably, most calculators, you'll need to set up the cubed root first and then begin to input what's under the radical symbol. And so we determine that x equals 0.0086. If you revisit the original question, we've been asked to calculate the equilibrium concentrations of all entities. Now that we know x, we know the equilibrium concentration here. We'll have to double it for this one and complete the binomial here. So go ahead and make your substitutions to calculate the equilibrium concentrations. Okay, and we finish up with concentrations of 0.38 moles per liter, 0.017 moles per liter, and 0.0086 moles per liter. Okay, the very last example follows everything the same, except we'll try the perfect square and it won't be there. We'll check the approximation and it won't work, and so we'll need to use the quadratic formula to solve for x. So the chemistry of these last three examples are identical, the chemistry. So if you're finding this difficult in the math, the solving for x, recognize that that's a math issue, not a chemistry issue, and you can isolate those skills and work on them on their own. But look back through each example for the chemistry of the problem. Okay, so you can try the last one, example number 4. Okay, so I set up the ice table after calculating initial concentrations and wrote the expression for K, substituted the algebraic expressions at equilibrium for the entities in the reaction. Now in order to solve for X, I'm thinking, is there a perfect square? And no, there isn't. The denominator is a problem. So this is a big no right here. Does the approximation work? That's my next thought. Well, does the initial concentration, so let's say 4, as I see for H2, divided by K, which is 50, is that greater than 100? And I don't even have to pull out my calculator to see that no, it's not. So the approximation's not going to work here either. So then the last choice is the quadratic formula. So I need to write the trinomial in the form ax squared plus bx plus c equals 0, and then use the quadratic formula to solve for x. Okay, and so there's a bunch of simplification to be done. So I'm going to square both the 2 and the x, so don't forget about that, so 4x squared, and then I'll apply FOIL to the denominator, and so 4 times 2 is 8, 4 times negative x, negative 4x, minus 2x, plus x squared. And now I'll simplify in the denominator there, so I have 8 minus 6x plus x squared, still a k over here. Now I have that trinomial in the denominator that I want to get it out of the denominator, so I'm essentially going to multiply it on both sides. And so I'll have the 4x squared here, and then I'll have the 8 minus 6x plus x squared, all multiplied by k. And now, since k is just a number, I need to distribute k. And maybe because k is only 50, you might find it easier to substitute that at this point. Actually, perhaps we'll do that. So let me just adjust here. Okay, and so we distribute the 50. So 50 times 8, we'll have 400 minus 300x plus 50x squared, which equals the 4x squared. So I'll swing the 4x squared over to the left side and reorder my terms. So 50x squared minus that 4x squared minus 300x plus 400 equals 0. And 50 minus 4 is 46x squared minus 300x plus 400 equals 0. Okay, so A equals 46, B equals negative 300, C equals 400, and I can go ahead and use the quadratic formula to solve for x. So x will equal the negative of negative 300 plus or minus the square root of negative 300 squared. This is b squared minus 4 times 46 times c, which is 400, and I want the square root of all of that. And all of that will be divided by 2 times 46. And so I didn't pick up my calculator until the very end. Don't waste your time. Use it once at the end. So the first time I'll run the root doing what amounts to positive 300 plus the square root of all this, and then divide by 2 times 46. It'll be important to use brackets. I'm going to need brackets here to close out the numerator, brackets here if I'm going to use multiplication here, and I'll need brackets underneath my square root sign. So I'm going to build those into the calculator as I do it. So I'll say it as I'm punching it in. So I open the bracket in the numerator, and the negative of negative 300, I'm just going to do in my head, that's positive 300, plus, now the square root symbol, and then open bracket for the negative 300 squared. Now that negative 300, I'm going to anticipate that squaring the negative makes it positive, so I'll just plug in 300 squared. If you weren't going to do that, you'd need to put brackets around your negative 300. Minus 4 times 46 times 400, close the brackets, and that's the end of that. Then I will close them again to surround the numerator, divide by, open brackets, 2 times 46, close the brackets, equals. And so I'm finishing here with 4.65 for one value of x. Now, that's x1, right? X could also be 300 minus the square root, and so I'll go back and do open bracket 300 minus the square root, open bracket 300 squared minus 4 times 46 times 400, close brackets, then close brackets again to close off the numerator, then divide by, open bracket, 2 times 46, close brackets, equals. And I finish with 1.87 here. Okay, one of these values will be inadmissible. What were we originally asked for in the question? If we back up, we were asked to determine the equilibrium concentration of HI, which is 2x, we can see. Now, the concentrations of H2 and I2 will be 4 minus x and 2 minus x. Is it possible for x to equal 4.65? The concentration of H2, even though we weren't asked for it, is calculated by 4 minus x. Aren't we going to end up with a negative concentration if we plug that in? We will, right? And so this can't happen. The concentration at equilibrium has to be positive. So 4.65 is inadmissible, which means that x equals 1.87 is our answer for x. So the concentration for HI comes in at 2x from our ice table at equilibrium. And so we just need to double 1.87 to get the concentration of 3.74 moles per liter. Okay, thanks for your patience. I'm sorry it was such a long one, but you'll have something to go back over now. Again, the math, I think, is what takes predominantly the bulk of this time. Just to let you know, for how I would mark this question, there would be marks for setting up the ice table. So calculating the initial concentrations and setting up your equilibrium expressions here. So your change row and your equilibrium expressions. A mark for substituting, or a mark for stating the expression for K, a mark for substituting. After that, all of this work literally is one mark. You're just solving for X. And then there's a mark in the end for calculating the concentration of HI. So the chemistry of the problem really is defined by the ICE table, the equation for K, and the initial substitution. The math of it is literally solving for X, so you get one value of X. Any error in there, right, will lead to an incorrect value of X, but if you show the substitution at the end for the equilibrium concentration, then you'll get the mark even if your final answer is incorrect. So yes, I'll give you part marks, and yes, it's not a math test, it's chemistry. The bulk of the marks will come from the chemistry of the answer.